This is the 45th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video explains what cache memory is and why it's so important. Here's the single-cycle CPU presented by the textbook. If we use these component timings given in the Harris text, we find that the CPU's critical path is 925 picoseconds, which corresponds to a clock frequency of just over 1 gigahertz. That's not a blazingly fast CPU, but it's not way out of line with what you would find in lower-end laptops or phones. However, this CPU design includes a little white lie. The instruction and data memory blocks don't really correspond to RAM access. The problem is RAM is slow. Really slow. It's slow for three main reasons. First, it's big. Managing billions of bytes of data is going to take time, especially when compared to the CPU's operations that are primarily targeted at a few dozen bytes at most. Second, the technology that allows these to be so cheap is considerably slower than other technologies for storing data. I'll explain in detail later, but for now, you've probably heard the adage, fast, small, or cheap, pick two. Well, this is just an instance of that trade-off. Third, data stored in RAM is far away from the CPU. Now, the RAM sticks themselves may be just a few centimeters away, but from the perspective of a CPU that runs at a nanosecond scale, the trip from the CPU to RAM and back takes a long time. Accessing data from RAM is like getting on the bus and going to Meijer when you get hungry, instead of just walking to the fridge. The best RAM today has a latency of somewhere between 10 and 50 nanoseconds. That may sound fast, but when you consider that many CPUs run at 2 to 4 gigahertz, a single RAM access takes somewhere between 20 and 40 cycles. Given those times, our 1 gigahertz machine can't possibly be making a RAM access during every instruction. If CPUs today were really accessing those RAM chips at 10 nanoseconds or more in access, today's CPUs would be more than 10 times slower than they actually are. So obviously the CPU is doing something to hide this latency. You're probably already familiar with the main trick that the CPU is using to hide latency because you do a similar thing every day in several different ways. For example, what do you do when you get hungry? My guess is that your typical response isn't to go get on the bus and go to Meijer, right? That takes too long. You just go to the refrigerator. Your fridge is just a smaller, closer place to store food. In some sense, your fridge is just a cache of food. CPUs apply the same principle by adding a small amount of very fast memory directly to the CPU. This cache of memory, hence the name cache, allows most loads and stores to be handled very quickly. Like your refrigerator, it's fast for two reasons. It's close. Just as your fridge is part of your house, cache memory is often integrated right into the CPU, in contrast to RAM, which is literally a bus trip away. The wires connecting the CPU to the RAM chips across the motherboard is called the bus. The cache is also fast because it's smaller. A typical level 1 cache is only a few kilobytes. It takes much less time to access 1 byte out of a few thousand than it does to access 1 byte out of a few billion. Right? This is analogous to it being much faster to grab a yogurt out of your refrigerator than to walk from the entrance to Meijer all the way to the dairy section in the back corner. Also, there's a third reason. This doesn't quite fit into our refrigerator analogy, but a cache is also much faster than RAM because it's built with a different, faster but more expensive technology. Let me be clear by what I mean when I say cache is more expensive. The technology used to build cache is more expensive than the technology put into the sticks of RAM you put on your motherboard on a per byte basis. But CPUs have much less cache than they do traditional RAM. So as a result, the cost of the cache is actually quite small. Let me show you what I mean. So today, the RAM that you would buy and put on your motherboard, called dynamic RAM, costs about $5 a gigabyte. And it's pretty common to find new computers that come with 8 gigabytes of RAM. So the total cost for RAM is $40. Now the SRAM technology used to build caches costs $500 a gigabyte. But a typical new desktop only has about 8 megabytes of cache. So even though on a per byte basis, the cache is 100 times more expensive, we're only using 1/1000th the amount of it, so the total cost is only $4. And this is the beauty of cache. We only need a small amount of it to get most of the benefit of this high performance memory. So it only takes a few dollars worth of cache to make a huge improvement in the overall performance of a CPU. So the way we leverage this is that what is shown in the diagrams in the book as instruction memory and data memory are really two separate caches. Let me also mention in passing that the fact that we have these two separate caches is what allows us to fetch an instruction from memory during the same cycle we're fetching data from memory through like a load word or a load byte. Okay, so now that we have these caches in the data path, we need to answer two main questions. What data do we put in the cache? And then when we go to do a load, how do we find the data we want? That will be the subject of the next video. For now, make sure you understand that RAM is slow because it's big, it's far away, and it uses a slower but cheaper technology. To mitigate this slowness, CPUs contain a small amount of very fast RAM called cache right on the chip. This cache technology is expensive on a per byte basis, but because we need so little of it as compared to regular RAM, the total cost is quite reasonable. So the purpose of this video is just to give you a very high-level idea of what cache is all about. It'll take us several more videos to get through the details.